Good morning and welcome to our first hands-on session on use of e-laboratory. My name is Vladimir Shensov and I'm a research associate in safety engineering working for Hydrogen Safety Engineering and Research Center at Ulster University here in Belfast. And today we are going to talk about some advances and what has been done during the last 16 months of the project. The project called NetTools, which is a novel education and training tools based on digital applications related to hydrogen and fuel cell technology. A few words about this project. It is aimed to develop an infrastructure and to provide digital tools and information services for educational issues and training within fuel cell technologies based on the most recent IT tools. So there are two main pillars, two main directions which we are developed in this project, which is e-education and e-laboratory. In this presentation, we are going to cover part of e-laboratory that was developed up to now, what engineering tools, online tools was developed, programmed, and available for testing on the platform. Now, so this is the overview of my presentation. I'll start off giving you introduction of the structure of the project, then continue talking through about the tools which are developed. Then we'll say a few words about the tools which are due to be developed within the next 20 months. Conclusions, and then end up with the questions. So you can type questions in the chat. I will be reading them, and at the end of presentation, I'll try to answer everything. If there will be some questions which are not related to me, I'll probably give a word to one of my colleagues who is participating in this WebEx. So please type your questions while hearing my presentation or at the end. It's up to you. I can see all your questions and everything you type. So the project, the consortium consists of 8 partners, so 8 different institutions involved in the development of e-laboratory and of e-learning. These are Karlsruhe Institute of Technology from Germany, a private company Percy from France, and National Center for Scientific Research Demokritos from Greece. Then Denmark Tankskin University from Denmark, University of Electrochemistry and Energy System from Bulgaria, University of Perugia from Italy, private company Element Energy from United Kingdom, and Ulster University. So this is the consortium. Here you can see the structure of the e-laboratory, which is the part of the whole project. And the e-laboratory consists of 2 main parts. This is e-engineering and e-science. This is 2 big toolboxes. And e-engineering is the toolbox which integrates different models and tools which are already validated and published, which could be used for fuel cell hydrogen engineering, for safety, and it is valuable toolbox for use in education, or for use by first responders, which could be used for it could be used by the people from who deal with hydrogen fuel cell installations, etc. Another toolbox is called e-science, which is more advanced tool which bridges different, more advanced research techniques such as use of CFD in simulations. So it's more like the first one, e-engineering, has online tools which you can go input data and get results, and the e-science has part which you can calculate online and the part which you can get the guidelines on use of CFD for fuel cell and hydrogen applications. Right. Altogether, there are 32 tools in total, which is due to be developed by the end of the project. In this presentation, we're going to cover 9, which are programmed and validated and available for testing. You already received the login and the link to the platform, where I hope most of you have chance to try them and use for your own purpose to calculate parameters which you probably might be interested in. And your honest feedback is really much appreciated. After this session, you will receive an email with a link for the questionnaire form, where we kindly ask you to provide your feedback, what needs to be improved, and what are drawbacks, and how we can make our platform better for use of whole hydrogen universe. So this is the way how it looks now. You probably already saw this when you went to the link and logged in. This is the whole bunch of tools we have so far, and we'll start off talking about the safety engineering tools. Safety engineering toolbox, and start with jet parameter model. This model allows you to calculate parameters of the flow at the exit from the tank or pipe, or whatever happens, like in case of accident, or if you need to calculate your flow rate for your particular installation when you have your pressure and pipe diameter. This model combines, it can be used for both expanded and under-expanded jets. And this graph, you can see the short description, where you can see the reservoir, where the flow velocity is assumed as 0, nozzle at number 3 point, and the pressure and velocity equal to ambient and local speed of sound, which is called notional nozzle or effective nozzle, at 0.4. And the 0.4 is only used when the jet is under-expanded. For expanded jet, the conditions are taken from 0.3 during the calculations. Now, every single tool has the scenario details already pre-filled, so that whenever you click on the tool, you already have some data which you can change for your own purpose and calculate your own task. So these are default values which we've taken from real scenarios to validate the model. And if you click on the link for jet parameters tool, you will be able to see the screen where you can input your orifice diameter, nozzle diameter, ambient pressure, and pressure in the tank. As well, you have to know the temperature in the tank in order to be able to calculate parameters at the notional nozzle and at the exit. There is also option for every tool where you can change your input and output units for temperature, length, volume, pressure. During the development of the e-laboratory, there will be new units added, so that anyone in the world who uses the NetTools and e-laboratory can use their own system. Every tool has the description, short description, where you can read about this tool, what it calculates, and where it actually comes from. It includes all the links to the publications, because every single tool is based on the publication which is validated. Whenever you press calculate button after inputting all parameters, you'll get the results for every single tool, For example, for jet parameter model, you can calculate what is the mass flow rate for particular pressure, what would be the temperature at the notional nozzle exit, what would be the velocity, effective diameter, temperature in the orifice, velocity, what would be the pressure. There is a bunch of different parameters which can be applied for different engineering purposes. So this is the place where you can, if you need to get, for example, density in the tank or density in the orifice, you can just go there, make a few clicks, and you will receive all results in one place. Now, another tool from safety engineering toolbox is the adiabatic and isothermal model for blowdown of storage tank dynamics. This tool allows you to calculate how the pressure in the tank changes with time for a particular nozzle, for particular orifice, from pipe or from TPRD or whatever. And since all hydrogen-powered vehicles have storage up to 70 megapascal, and at refueling stations it's even more than or about 100 or 1000 bar. Unignited release from such high pressure can create highly underexpanded turbulent jet. And the majority of the leaks and storage vessels and equipment are taken in the form of unignited jet, and during the tank blowdown, it will end up with expanded. So this model incorporates both underexpanded part and expanded. So this is the scenario details which we use to validate the model and to check that we are getting the correct results for both cases. And yes, there are two options, adiabatic and isothermal. So in this presentation we'll cover adiabatic part. It's pretty much the same in terms of interface. So I'm not going to cover isothermal. Description here again shows you what is the model based on all publications and how it works. After input all the parameters for the pressure in the tank, temperature, tank volume, diameter of TPRD or a pipe, temperature and pressure, you can get the full dynamics of tank blowdown. You can see on the graph that for 205 bar, the blowdown to zero from 9.5 millimeter pipe happens in just about 20 seconds for nearly 200 liter tank, which is quite fast. So changing parameters, you can calculate what time would require to blow down, let's say something bigger like transportation lorry, big tanks, or smaller tanks, and you can play with the values and see in terms of the time by changing the orifice diameter, and this gives you the feeling how long time you need to, let's say, if it's indoors, what kind of ventilation rate you need to let's say extract this amount of hydrogen from enclosure. The output parameters gives you everything starting from how mass changes in the tank, how density changes with time, what is the pressure and how it changes in the orifice, density in the orifice, how temperature changes everywhere inside the tank, inside of the orifice, and how changes the effective nozzle diameter, which could be used for CFD applications when you want to simulate real scenario and you want to make dynamic notional nozzle change, etc. So it's quite flexible tool. Yeah, whenever you press the plot button, you are able to see the graph, or you can export to CSV file, which can be then used in your own purposes. You can save it on your computer, or you can save the data set for on your account. At the moment, we have created the common account for all users of eLaboratory, but in future, everyone can go and get registered for free and create their own account where all data and all calculations will be saved for every single user. Moving next, we have flame length correlation and 3 hazard distance for jet fires tool. This tool allows you to calculate the flame length based on the diameter of the release and the pressure in the tank. And this tool uses the dimensionless flame length correlation and all the links provided in the tool description. It's only dependent on the parameter of actual nozzle exit and on the density of the surrounding air. As you can see on the graph here, the parameter LF, which is flame length over diameter, changes and increases for laminar and transitional flames, buoyancy controlled. Then it's practically constant for transitional and fully developed turbulent jet flames, momentum dominated. And it again increases for under-expanded jet. And the separation distance or hazard distance, it was calculated using the light chance publication based on 3 parameters, which is no harm, the distance of 3.5 of the flame, the pain limit, which is 5 minutes exposure at 3 distances of the flame length, and the third one is the third degree burn of after 20 seconds of exposure at the distance of 2 flame lengths. This correlation was implemented and used in the tool. This graph shows the flame length and hazard distance for 5 different nozzle exits, starting from 1 millimeter up to 5. And you can see that the nozzle diameter is proportional to the flame length, and the smaller the nozzle diameter, the shorter will be the hazard distance. In the table below, we have the distances for of the flame for each nozzle for each nozzle diameter and the separation distances. Initial parameters was taken for 350 bar storage and ambient temperature and pressure. And that's the way how the tool looks like. All the tools are made pretty much they have the same interface, where you have option to change the units, where you can always read description if something not clear, and proceed and read more about every tool by clicking the appropriate link in the tool description. So as I said, we had a 350 bar tank and let's say 1 millimeter diameter, and the results looks like this. You can see that the flame length for 1 millimeter diameter of the nozzle at 350 bar is 2.6 meter, while the separation hazard distance changes according to the light chance. No harm at 90.1, pain limit 7.8, and third burn at 5.2. The next tool from Safety Engineering Toolbox is the similarity law for concentration decay in hydrogen expanded and under-expanded jets and unignited jet hazard distances. So this tool allows you to predict concentration decay of hydrogen for subsonic, sonic, and supersonic unignited jets. It's also used to calculate the hazard distance formed by the size of the flammable envelope based on the 4% concentration. The correlation is shown by the formula, where X is the actual distance from the nozzle, D capital is the nozzle diameter, Then rho n is the density at the nozzle exit, and the rho s is the density of surrounding air. As well, CAX denote as the mass fraction of hydrogen at initial distance x. And this tool allows you to calculate distance from the nozzle to 4, 8, 11, 16, 29.5 stoichiometric, and plus you can specify your own concentration in range from 4 to 75% and calculate the distance to this concentration along the axis. This tool utilizes hydrogen jet parameters model for under expanded jet and use isentropic pressure and density relations for expanded jets. If we proceed to the tool description, we can see on the left, again, tool description, unit change, input parameters for pressure, temperature, diameter of the orifice, ambient temperature and pressure. And you specify here the percentage which you are looking at. For example, we put here 20%. And after calculation, you can see that the screen shows you percentage to the distance to 20% is 5.5 meter, and the whole range of distance is starting from 4% to 29 to 29.5. Hold on a second. Yes. And to 4% is basically the hazard distance based on the hydrogen envelope. 32 meters for 5 millimeter orifice diameter and 350 bar, which is quite long. The next tool here is the passive ventilation in enclosure with one vent for uniform hydrogen concentration. Why passive ventilation? Because it's different from natural one, and natural ventilation assumes that the flow through the vent is equal. So inflow of fresh air and outflow of from the enclosure is the same, and this flow is separated from so-called neutral plane. And it was shown that the natural ventilation equations underestimate concentration by 2% for lean mixture, twice for lean mixtures. You can see here that it's twice higher, twice lower underestimation for lean mixtures, and overestimates twice for rich mixtures. The nomogram was also developed and online tool to calculate the maximum concentration for steady-state leak in enclosure with one vent. The passive ventilation, in case of passive ventilation, the neutral plane can be anywhere compared to the natural ventilation from the center of the vent up to the bottom, and it can even go below if the mass flow rate is very high. One of the examples you are looking at is that the maximum normal hydrogen discharge for permeation from fuel cell leaks allowed to be about 150 normal liters per minute per car, which is the mass flow rate of 2.1 by 10⁻⁷ kilogram per second. And with this mass flow rate, for the vent, for a garage vent, let's say, of brick size, which is 25 centimeter by width and 5 centimeter by height, will give us about 4% concentration and at steady state inside of enclosure. But since the ventilation rate for natural and passive ventilation is proportional to the area of the vent by square root of the height, the difference for the same area, if you put make it not horizontal but vertical vent, the efficiency will increase by 2.2 times, which will reduce the concentration of hydrogen and probably will allow high permeation rate. This also has to be taken into account while doing hydrogen safety engineering, especially for natural ventilation systems or passive ventilation systems. This is the nomogram, which is the graphical representation of the tool. The set of equations are shown on the left, and if you, for example, need to quickly assess what would be the concentration in the enclosure of this particular with this particular vent, and if you know what would be the hydrogen flow rate for the given installation, you can use this nomogram and calculate on site. The example is given for 1 gram per second, which is equivalent to about 50 kilowatt fuel cell or light duty vehicle. And the calculation example shows that you start with selecting the release rate 1 gram. On the bottom graph, you select the height of the vent. Then on the right top, you select the width of the vent. Let's say we have half meter height and 1 meter width. Then you drop the line to the function curve, and you'll get that the concentration for this particular vent with this flow rate will give us unacceptably high 13.6%. You can use this nomogram either way around and calculate starting with what concentration you need. Let's say you start with 4%, you drop the line to the function curve, you select the ventilation vent width, and you drop the line to the ventilation height, and you will receive what mass flow rate you can allow. Or you can calculate the width or the height of the vent. So it's quite flexible thing, which can be used anywhere by use of pencil and a ruler. But if you want to get, it has some kind of error, of course, because it's graphical, it probably will give you 5 to 10% error. And if you want to get exact results, you would need to use the tool. This nomogram will be available to download and print shortly with the development of the tools. But for now, you can only go and calculate all the parameters from the laboratory. You need to specify ambient temperature and pressure, the discharge coefficient for the ventilation. Discharge coefficient shows the amount, the area, the effective area of the vent which is used for ventilation. The default value is 0.6, which is commonly used, and it's validated value. However, for different vent parameters, it can be different. In this case, we select an input 1 gram per second release with half meter high and 1 meter width, and we got this 13.6% of hydrogen for the enclosure. For 13.6 concentration, uniform concentration of hydrogen in enclosure. Next tool is pressure peaking phenomena for unignited releases again. And here, these tools give you the pressure dynamics inside the enclosure in case you have unscheduled release. Because all the hydrogen vehicles which are kept inside of the confined space can cause this hazard, and it was proved, and there is a number of publications done on this. And this can result in really high pressure inside of the enclosure, which could create major damage or even collapse. Let's consider the unignited case for high pressure tank through the orifice, or the TPRD, which can be triggered due to fire or to malfunction. And this model is based on the adiabatic and exothermal release. It can be used both. Also, it uses the model for hydrogen jet parameters model to calculate the flow rate from the tank. And again, it's both valid for expanded and unexpanded jets. Okay, this graph shows you the overpressure effects on buildings and humans. And as you can see, the overpressure of 0.2 bar or 20 kilopascal is capable to destroy residential structures and make them collapse, while causing serious injuries and common fatalities to humans. The scenario details are taken from the most common garage of 35 cubic meters volume, normal temperature and pressure, typical single brick vent size, and the mass flow rate for 350 bar storage tank with 5 mm TPRD would give nearly 0.4 kilogram per second of hydrogen. These parameters we use to calculate pressure peaking for constant mass flow rate. There are two options in this tool. You can specify constant mass flow rate, or you can calculate the blowdown of the tank. And the figure here shows the comparison of the constant mass flow rate and tank blowdown. And both of them, for this particular vent size, give us more than 20 kilopascal. So while doing hydrogen safety engineering, I think it is essential to check whether your ventilation parameters are sufficient to withstand pressure peaking phenomena. And this tool is quite flexible to assess the dynamics of pressure inside. You can combine all the areas of your ventilation. It's not only for one vent or for two vents. You can combine all your ventilation openings and calculate total area, and you can specify the pressure inside the tank storage facility. You can specify diameter, and in the end you will calculate your pressure dynamics as well as the mass flow rate and overpressure. Yeah, that's what I wanted to say, that at this level of overpressure, most residential buildings will collapse, and this will cause serious injuries and possible fatalities to the humans. The next tool is the effect of buoyancy on decrease of hazard distances for unignited releases. The tool shows you the effect on the hazard distance due to the buoyancy. So we have three types of jets. Momentum controlled, when the buoyancy is not affected. Then the one which has momentum part and the buoyant part at the end, and fully momentum jet. And this tool is calculating the distance from the release nozzle to the concentration at which release changes from the momentum controlled regime to the buoyancy control. It also gives you the hazard distance to concentration of 4% by volume. And another feature is you can calculate the vertical downward release and the distance and concentration at which the flow starts to go up due to the buoyancy. This is how the tool looks like, and you need to input the pressure of the tank, temperature, and diameter. After calculation, you will get the distances to every concentration, and to all concentration you can specify 4, 17, which are predefined: 4, 17, 30, 40, 50, and 60, and you will get the distance to these concentrations, and you can calculate the distance from to the turning point or for the downward release. Now, we move into the next tool, upper limit for hydrogen inventory in the closed space. This tool is the model behind this tool allows you to predict the mass of hydrogen, which can be and may be allowed to be released inside of enclosed enclosure, without causing any destructive overpressure. And the model assumes that the enclosure is filled with hydrogen and air at initial pressure. And if the hydrogen-air mixture which is present in the enclosure is burned, the solution of this equation will result in absolute pressure, which can give you a clue whether you are on a safe side or not. And this tool allows you to calculate these transcendental equations, to calculate the mass of inventory for the given overpressure and enclosure volume, or to calculate the volume for the given overpressure and inventory mass. So it has two options. And both two options are shown here. For example, you need to calculate what mass of hydrogen in enclosure for, let's say, 35 cubic meters you may allow not to exceed overpressure of 10 kilopascal. You put temperature, ambient pressure, overpressure which you want to not to exceed, and the enclosure volume, and it will give you around 8.9 grams of hydrogen can be safely released and burned inside of enclosure of 35 cubic meters. Other way around, if you need to calculate the volume of enclosure, which you're probably looking to withstand certain overpressure, and you have particular amount of hydrogen you want to store, whether it's warehouse, something really big, or it's a small garage, you provide values for the overpressure and the mass, and at the end you will have the enclosure volume. So it works in both ways. So the first 8 tools were about the safety engineering. Now we are moving to the next section, which is fuel cell integrated into CHP. And this tool was developed by our colleague team from University of Perugia, but due to overlap with other meetings, they are not capable to talk about this tool, so I will be talking on behalf. So this tool allows to simulate the fuel cell integrated into CHP application, and including the electrolyzer. So the model behind allows you to calculate the payback time for the fuel cell combined heat and power unit once it is installed in the building. It helps you to understand and evaluate the convenience and the profit you can get from installing the fuel cell technology inside your house. Additionally, this tool also can consider integration of renewable energy source, such as solar panels, wind turbine energy, and in such case, an electrolyzer and the hydrogen storage solution was also considered in this tool. We have 2 sections where you have standard CHP application and integration of the renewable energy source as a section number 2, plus hydrogen storage evaluation. The purpose of this tool, it is developed for engineers, technicians who are not confident with technology that was to evaluate the performance of micro CHP based on fuel cells for an existing building or a new building, estimating the energy consumptions. The private investors such as ACOs, ESCOs looking for convenient technology for energy and heat production. Private citizens that can calculate based on energy consumption and cost for their house, and to see the economical feasibility of changing the existing boiler with a new, more efficient system. Students from university who can use this tool for the training purposes in order to predict and design new CHP units based on novel fuel cell technologies and maybe new technologies, etc. For inputs, you have monthly electricity and heat consumption, efficiency of your boiler, and CHP inputs would give you the unit size, thermal analytical efficiency, unit cost. The market inputs, you would need to use electricity cost, retail price, and the cost of the gas. And for integration strategy, you use utilization factor of the unit during the year. So basically, it's the depreciation per year. In section 2, you have monthly utilization factor, power usage, and unit cost of RES, renewable energy system. Storage units, you have electrolyzer, fuel cell efficiency, unit cost, hydrogen storage unit cost. And as a result of calculation, you can see the payback time in years and what are the energy flows during the year. That's how the units for input looks, and you can see their table, which gives you every month the usage of energy, and you can also see the graph with the gas cost and the payback in years, which is around 5.3 years for these particular inputs. To be honest, I'm not kind of familiar with this tool, and I probably would need to talk to our colleague from Perugia, but looks like he is not here, so I will just simply continue. Tool gives you at the end of calculation, you probably can get this kind of tables where you can see the contribution of renewable energy sources and fuel cells, and the payback to include renewable energy sources is increasing because you need to have storage and solar panels or wind turbines. Depends on your inputs. So there was 9 tools covered during this presentation, and within the next slides I'm going to be quickly cover what other tools we are going to develop within the next 20 months. Within the safety tools, we are looking at another 7 tools. There's somebody dealing with his mic. All right, and there is a number of tools in e-science, in high foam, and e-engineering. E-laboratory of engineering toolbox will have another mitigation of uniform mixture deflagration by venting technique. So this tool will allow you to calculate the vent area required to reduce deflagration overpressure to a given level, or estimate overpressure for a vent of known area. So if you, for example, have a warehouse or hydrogen installation system with ventilation, you can calculate what would be the overpressure for the ventilation uh, when you release certain amount of hydrogen inside, or you can calculate the vent required to mitigate the overpressure. Another tool is the forced ventilation system parameters, and this one will allow you to calculate ventilation flow rate of air required required in a steady state regime to get desired concentration of hydrogen based on the gas release inside. Another TPT tool is the blast wave from high pressure rupture without and with combustion. So this tool would allow you to calculate the blast wave from tank explosion, whether it's underneath the car or it's a standalone tank. Will it have a contribution of combustion, or it will be just physical explosion without fire? Then the pressure peaking phenomena for ignited release will give you the pressure dynamics inside if the jet is ignited. So it's for jet fires indoors, which are more pronounced compared to unignited releases. The effect of buoyancy for the hazard distance for jet fires as well. Another tool which is continuation of the tool for buoyancy effect for unignited releases. In terms of deflagration, there will be another tool for mitigation of localized non-uniform mixture, and this one will allow you to calculate the various parameters like area, overpressure for the enclosure of the given volume, and a certain amount of hydrogen released indoors. One of the last tools for safety engineering toolbox is the calculation of fireball diameter. In case of the tank explosion, it's either standalone tank or on the vehicle. The fireball is different, so user can select the location of the tank, whether it's just experimental setup or it's real case when the tank is underneath the vehicle, and calculate the diameter of the fireball of engulfing fire to understand what are the hazard distances associated with this hazard. Among property tools, there will be a tool for calculate of the compressed gaseous hydrogen storage, and it will allow you to calculate volume and density of hydrogen inside the tank. And in terms of CFD application, there will be a number of guidelines and examples to be given for different applications of so-called high foam, which is open source code for CFD applications. And there will be 5 tools, 5 cases described, which is release and dispersion of horizontal under expanded hydrogen jet. This is the HSL experiment. Large-scale deflagration in an open atmosphere, Fraunhofer. Blast wave and fireball from high-pressure tank rupture in a fire by wind. Then hydrogen release and dispersion in vented enclosure, and the vented deflagration case. So there is a lot of work to be done, and so far this is our first beta version. It's not yet embedded into the platform. It's not available to the public. It's only available for a small group of people who can test, look, find some bugs. And the aim of this webinar was to introduce you to this platform, to the kind of first step what you made during the last month of working on this project, and to receive feedback, positive, negative. Every feedback is really much appreciated, and we are aiming to make it as best as we can. So we have 32 tools altogether to be delivered by the end, and 9 tools already developed and deployed, and the new one will be added as they become available. And the next hands-on session is planned by the end of the project. It's within the next 1.5 years. There will be another one. So I really encourage all of you to keep in touch and subscribe for our next hands-on, where we hope where all tools will be here, and it probably will change the idea of the webinar, and maybe we'll be working and as given examples, so then you can calculate and more like in the way more interactive, I would say. So this is the end, and I would really like to thank everyone in the project, to my colleagues from Percy who was developing all the tools, their main developers, so people from the consortium, they provide in the description, and thanks to Adrian from Percy, to Lawrence for the technical support and programming of all these tools. And thank you very much all who found the time to be here. And yes, of course, for European Commission for Financial Support. And please subscribe for our newsletter. Keep in touch, send me emails, questions. I'm happy to answer all your questions. And now I'm ready to proceed to question and answers. I don't really see more questions so far in the chat. So if you could start typing your questions, I will try to answer them. Okay, there is a question. What is the advantage of jet parameters model while the blowdown model is considering all of them in dynamic scheme? Blowdown model indeed is a dynamic model which can give you how the pressure, density, and all parameters changes inside the tank and in the orifice. Jet parameters model give you particular values for steady state condition in the nozzle. Both of them indeed based on the same methodology and same idea, but the blowdown is an extension and used for application for tank blowdown. Let me read all the next questions. Talking about the CD, this discharge coefficient, the publication, which is so the model is based on publication where we tested this CD, and there were about, I don't know, 48 experiments where this model were applied, and there are few coefficients. One is conservative and one is the best fit. So for the best fit, we chosen the one which is widely used of 0.6. So that's why it's in the model, and of course you're free to change it to adjust your calculations. No problem. That's why it's there. Yes, the pain limit for 5 minutes is 115 degrees. system is quickly depressurizing and the consequent jet length is reducing accordingly. Yes, that's correct. However, I cannot get where this is for which tool. That's for the flame length. In the case of the flame length, we have steady state parameters at the nozzle. And that's actually a good point, and probably we will try to add this option so that we can see the dynamics of the flame length. However, for engineering purposes, we better to be conservative and see what's the maximum flame length for the particular pressure and diameter. The third burn degree is for 20 seconds, yes indeed. In terms of fatality for the flame length correlation, indeed it is not yet mentioned, but I would say after 20 seconds close to the fire, you are really close to fatality. So we shouldn't aim to reduce hazard distance to the fatality. We are more likely to better make it further rather than bring it close. Yes, indeed, only one direction towards the jet axis. However, you can calculate the flame width by multiplying the flame length by 0.17, if I'm not mistaken, to get the hazard distance from the side of the flame, which is a good point, and I will take a note on that, and maybe we'll add another options to see the width of the flame for that tool. Thank you, Bernard, for your comment. Yes, the property tools will be ready shortly. It is now vacation period, and it's not that intensive work right now, but we are working on that, and property tools already have descriptions. It's just a matter of programming. Quite a big load so far. I'm not quite sure I understand the question about the initial pressure state. So, and for which tool the question is about, because every single tool has initial pressure. Eventually, if you're talking about the blowdown tool, eventually it will reduce to 0, of course. But in steady state, it will not reduce to the 0 because it will be steady at 350. In terms of the similarity law for concentration decay, how these concentration distances relate to the real consequences? If you calculate it wrong, and let's say you place ignition source in the vicinity of the hazard distance, and your flammable envelope will reach the ignition source, then you'll have real consequences. So you always have to be careful about calculation where your hazard distance located from the release source. As an example, Baker's triple methods or multi-energy methods most applicable for hydrocarbons. Give the dimension of the cloud and then based on the level of congestion they provide a distance based over pressure. That's kind of suggestions if I'm not mistaken. Okay, I'll take a note on that. Does anybody have more questions so far? No. So initially we plan to have 2 hours for WebEx, but it looks like we don't have much discussions or no questions. There could be for two reasons. Everything was clear or nothing was clear. So yes, Nicholas, please rephrase the question. No more questions so far? Okay. So for what harm limit, the steady state you refer to is if the tank pressure is constant at 350 bar. That depends on what kind of harm criteria you select for your installation. So if you're looking at not to ignite, but okay, everybody not want to ignite, so the harm limit is not to exceed 4%. We are talking about the concentration decay tool. I'm a bit confused with this question again. $350 was just an example case. You're free to select any pressure and calculate your harm limit. So that's not a Bible which you can follow, which you should follow. All right, it looks like no more questions coming up so far, and I would like to thank you all for coming and listening to me. Hope you enjoyed this session, and hope to see you next time. Thank you very much. All the best.